Please.
At MIT we have two types of courses. The service courses and the rest. In the rest you present whatever you want and usually it's attended by small group of students. But in the service courses you have to present certain minimum and it's attended by many students and it's used in other courses. So actually my course is the service course. And by the way, for the service course at MIT, professors get reduction in future teaching. So I hope they will get some reduction. Since I want to present quite a bit of various things, I decided to speed up a little bit, in particular in the proofs. Proofs I will very often skip if they're very straightforward. But I will state precisely. It was already in the first lecture that I stated the extension theorem, which basically says that if you have something which can be called as a free-vertex algebra, it's a little bit similar to free-shift, which consists of this data vector space, a non-zero vector called Vacuum vector, C operator in this vector space, and F a collection of quantum fields which satisfy this axiom. Then it can be extended to a structure of a vertex algebra, a unique. But in fact, something even stronger holds. And let me state this full formulation of the extension theorem and then prove. Let F minimum be the following collection of quantum fields. It's span of all quantum fields which are obtained from this generating set F by the n products. L1, L1, L2. You see, it is exactly corresponds to elements of V which span it, and we take S products from right to left. First, the corresponding NS field applied to I, then the previous one, etc., and then at the end the first one. So, if minimum is certain collection of quantum fields, because we proved that N's product of quantum fields is again the quantum. And then F maximum is the thing which I introduced in the first lecture. It is all translation invariant, covariant quantum fields. Of course, translation covariant means with the second property, which are local with each field J runs over some index F possibly. And here it's for example. Then the statement is the first F minimum is equal to maximum. Just to feel that two systems interacting quite differently. B, the map which we call field state correspondence, that's what it's FS, which associates to F minimum. Now F minimum maximum is the same, so we can write easy also. Which we defined last time, but let me remind you that quantum field F of Z, A of Z goes to the following state. You take A of Z, apply it to the Latin, and then put Z equals. Is well defined and bijective. Well defined means that you can put Z equals. Denote the inverse map by state field correspondence. So to every state A, the associated corresponding constant field. And finally C, the Z product A of Z apply to B, A of Z B, which by definition is this. You take state which corresponds to the field you take SF of A is field. You take the field corresponding to the state A, and apply it. And does B with the structure of objective algebra, extending the previous. Last time I proved okay, for the proof denote by introduce yet another set. It's called F translation Hawaii. It's just all AOT, the quantum fields AOT such as CAOT. The set of all translation covariant quantum fields. Then dilemma 2. If you remember, if you have such a field for any of the for the translation covariant quantum field, the field state correspondence is well defined. Namely, if you take AOC and apply to the vacuum, then it is the form of our C is 3. So you can put Z equals and field state correspondence of AOC is the well-defined element. So the next lemma, and I will remind the lemmas from last time. The space of translation covariant fields contains the identity operator, is closed, is CC invariant, derivative of translation covariant field, and is closed under all nth products. Proof just straightforward. Observe that we have the following proof. Of the spaces of quantum. First of all, the collections that we began with, this previous subject, is the smallest, and it's containing F minimum. F minimum is contained in F maximum, and F maximum is contained in F translation covariant. So let me explain you why. This holds because if you take A of Z and take minus first product with a vacuum, it is just normally ordered product of two fields. So this is identity. Normally ordered product of identity operator and then one two field is a split product of quantity. Now the next inclusion, this is by Dong's lemma, which says that nth product of two local quantum field is local with each other. So we get so we get that it has a locality problem, and by lemma 4, we still have translation covariance. So and this is by definition. Of course, it's clear that this is, of course, much larger than this. The theorem claims that these two things are equal.
What do you mean by definition? Maybe the last inclusion is by lemma 4.
No, F maximal consists of translation covariant fields. And so the question is whether this is, somebody asked me the question, is it, maybe you just take all translation covariant fields? Of course, this you cannot do because, for example, the order at RT is a translation covariant field. So it lies in that. Because what? Because T comma T, this is applied to T, and both are zero. But of course, T is not local to any field which depends on T. But T is not local. So this space of fields is actually much larger. Okay, next. Lemma 5. Altogether it will be 7. Let A of C and B of C be translation covariant fields. Let A be the state corresponding to the field A of C, so you write field state corresponding. And B state corresponding. Then, first of all, if you take field state correspondence of the identity operator, it is a vital. B, if you take field state corresponding to the field BZ A of Z, you get the state C of A.
Not zero, vacuum.
Sorry. And C, if you take field state corresponding to the field A of Z as product with the P of Z, you, as you expect, get state A and the S product of the state for any and the proof is again straightforward, so I next is dimension 6. Which says that which is the following. So let A of Z be translation covariant. Then we have the following properties that if you type conjugate A of Z by E to the W of T, so you take you get the formal distribution and divide distributions in two variables, Z and W. So then it is equal to the formal distribution U of Z plus W. But since here there appear also negative powers of Z plus W, you have to say in which domain is expand. And you expand is the domain AZ W. So obviously both are okay, cool. Both sides are elements belong to angle B. This take infinite in both directions series is the inverse. So dependence on Z is just this. But the dependence on W is just the formal power C. So this is formal power series whose coefficients are elements of the formal distributions and divided for formal distributions in one way. Why it is so? Because obviously this depends in W as a formal power series, there are no negative powers of W. And here, since you expand in this domain, there are negative powers of Z, but no negative powers of W. And both satisfy differential equation in Z. No, in W. D f of W dW equals Ft taking formula applied to f of W. With initial condition f of 0 equals, so if you put if you put W equals 0, of course you get A of C. So it's the same as the proof of lemma 1, which I haven't used yet. It's just existence and uniqueness of solution differential equation over formal powers. And finally, the last lemma. Lemma 6.
7.
Lemma 7. It is a uniqueness lemma. In my book I have a similar lemma, a little weaker, which I call Goddard uniqueness theorem. But it's a little strong. It says the following. Let f prime be a collection of translation covariant fields be such that the state corresponding to any field A of, to a field A of Z is 0. For some field, quantum field. It's first property. And second property, that A of z is local.
I don't understand. What is this property? For A of z in F for every.
Yeah, let A of z, let F prime be a collision with such line field, and let A of z be a field.
In F prime.
No. Some whose, for which the corresponding state is equal to 0.
So it's not B such that N let.
Let F prime be in Z and A of Z a quantum field. Such two properties hold. First, state corresponding to A of Z is 0. And second, A of Z is local with all fields from F prime. Yes, it's three properties. Second, A of Z is local with all fields from F prime. And third, if you take states corresponding to all fields from F prime, you get the whole thing. The conclusion is that A is 0. Probably I have this space to prove. Yeah, proof is not entirely obvious, that's why I give you the details. So let B you see in field from F prime. The locality we have, since A is local with A and B, we have the Z minus W to some power N. We write it like this. B of W B of Z is equal to Z minus W to the M A of Z B of W. Of course, you're already smart enough to know that in the super case you have to put here plus or minus sign. What else? Now apply both sides of this equality to the y. Now I use lemma 1, that A of Z applied to the vacuum is always equal to, for any translation covariant field. Did I say that there is translation covariant? A of Z is F translation covariant. Yeah, иначе, yeah. Then otherwise you even wouldn't be able to apply it to y. So it is e to the tz applied to A, where A is a state corresponding to AFC, which is zero, the condition one. So left hand side is zero. Now what about the right hand side? FAC minus W to N. And then again you apply no, you just rewrite it. Is equal times A of Z U of W apply to the. But now the right hand side is the formal series in W. Therefore you can put W equals 0. Of course, the left hand side is still 0. If you do that, you get Z to the N times A of Z applied to B. B is the state corresponding to 0. So now you can cancel Z to the N. So you get that A of Z applied to B is equal to 0. And I did use only the last condition that the state corresponding to a prime contain all B. So we conclude that it's true for all B. Then there's something which proves that. Okay, now the I thought that you need to use Lemma 6, but apparently you didn't need. Okay, but we'll use it. Okay, so now the proof of so this yes, there was another coefficient eraser.
Just above you on the right side.
So broken. Extension. First, we prove that the map field state corresponds from F minimum V is surjective. This follows by lemma 5 A and C. Because what is image of the field from where is that minimum. It is big. So you take AJ1 of the 1, AJ2 of the 2, so from right over AJ S, and you apply it to the right. And now you apply field state correspondence. If you apply it, then by lemma 5a identity goes to the vacuum. And nth products of fields goes to nth products of the corresponding Fourier coefficients. So you get A times S, etc. A into A and 1. But this is spans V by the complete transaction.
You forgot the upper indices.
What?
You forgot the upper indices.
Okay, so this is next. The field state correspondence from F maximum to V is injective. By the uniqueness realm. What the uniqueness realm says, that if you, by taking F prime equals to F minimum. So what is the condition? That F prime are translation covariant. And secondly, states corresponding to F prime consist of all vectors of V. And we just proved that it is okay. Therefore, if you take arbitrary AOT from F max, it is in particular translation covariant, so all conditions of Riemann 7 hold. Therefore, if the image and the field state correspondence is 0, then the whole quantum field is. Uniqueness lemma says that quantum field from F max it's determined completely by its value on the right. Okay, so we have that the field state correspondence on F minimal is injective and is surjective on F maximum is injective, but F max is bigger than F min. So it is injective here, therefore it's injective here. And it's surjective here, therefore it's surjective here. So the conclusion is that F min is equal to I guess, so what was the statement be? Is it lemma 5?
That F is bijective, which is
bijective.
Which is here. Proving A and B. No, but it's already written. It's already written in the next line.
I see. So, okay, so this proves now what they're equal. But now, since they're equal and it's surjective on F max and injective on the other way around. Anyway, it's both injective or projection, so we can prove at the same time. And finally, defining the Z product by this formula A of Z times B, you take field corresponding to A and apply it to B. White is a vertex algebra, because all axioms hold. What were axioms? There was locality axiom, translation covariance axiom, which hold by definition. So I think vacuum axiom. But what is a vacuum axiom? That vacuum acts as identity. This was one of the properties which were clear. It is this. It is lemma 5A. And the other is that what happens if you apply A of Z applied to the vacuum. But this is by lemma 1. Is that it is e to the zt applied to the vacuum, so it is applied to A, which is A plus ct applied to A plus A. And that's exactly the definition of a unit of Z algebra. So all properties of a vertex algebra hold, and this completes it. So apparently I never used lemma 6, so okay, so it's easy. But I will use it to derive some properties, further properties of the vertex. Let me derive corollary from it, and then I will make it. Corollary from the proof. First of course, it is explicit construction of the state field correspondence. If you take state field of A 1 and 1 and 2 and I get J and 2, etc. A and S, G, S, and Y to the vacuum. Then it is the following field. So you take A, field AJ 1 and 3, takes us and first product, gives the product AJ2 and so on, AJS and what is it? So we have this very explicit construction of the field corresponding to this state. And if the state spans the whole vector space, that we have explicit construction of the state field corresponding. And note that from the proof it follows that this formula is well-defined map, because you can represent the same element in many different ways as such a product, but still the elements that you get is. The second property is that if you take a field corresponding to TA, it is simply the derivative of the field over V. And finally see that if you take the field corresponding to nth product A of A, it is the nth product with the field A of Z. So the proof of this, take S equals 1 and N1 equals minus 2. Then we know that field corresponding to A minus 2 with vacuum is TA. And and here you have minus second product, which is derivative normally of the product is identity, but normally product is identity is the same. So this is proof of B. And proof of C, just take S equals 2 and 1 equals N and 2 equals minus 1. Then the minus first product of field with vacuum is the field itself. So you get just nth product of two fields. You take field corresponding to nth product, and this equal to the nth product. Yeah, and the final remark, which has been already mentioned, I think it's the talk of Fede, is a special case when all these nth products, a special case of A. What is the state field correspondence of an element AJ1 minus N1 minus 1, AJ2 minus N2 minus 1, etc. AJS MS minus 1. Reflected. Just what is N first product? N first product is just you take AJ of Z, you just take normal order product. Here you have to take N first derivative, dz to the N1, dz to the N2, etc. dz AJS divided by A1 factorial, etc. And in many cases, like the vertex algebras associated to formal distributional algebra, like affine of level K with Rasor of central check C, this always holds that these elements span the whole space. So you can define the state field correspondence by this formula always. And the only thing, important thing to remember the normal ordered product, of course we define normal ordered product of only two fields. But for n fields, it is just taken consecutively, but from right to left. Let me write like this. AHV, for say, UHV CLT. Normal from right to left, this means that you take normal product of DLT with CLT, and then normal the product of this is CLT.
So you meant n1 factorial, ns factorial, because these are indices.
Yeah, you just divide by this product.
No. But it's n, it's not j.
N, letter N, N, because j is an index of the field.
And 1 and 2.
So divided by factorial.
DC and yeah, and S.
And then you divide by factorial of
n.
Factorials of n. Yeah, that's right. And 1 factorial, etc. N. Okay, now let's make it work. Is there no other information? It's called nth product identity, and we'll use it. By the way, I just erased formula where at the end I had ns product with vacuum, but in fact I meant field corresponding to the vacuum, which is identity. So you have to replace vacuum here. Now another corollary is the following. If you take by V denote by V the set of all the span of all ANs, where A is in V, N and V. Of course, each n is an endomorphism, so it is a subspace in NV. Is a subalgebra of the Lie algebra. Of course, in the case of superalgebra, there is a sign. Why is it so?
You mean GLV?
What?
You mean GL?
Yeah, I mean GLV.
Sure.
And similarly, in this case. Why is it so? Here I reminded you the commutator formula for arbitrary formal distributions. It's given by this formula. But in the case of vertex algebra, remember we have nth product identity. So in the case of vertex algebra, this can be rewritten as this, because nth product of quantum fields corresponds to quantum field associated by field state correspondence with j's product in P. And this can be cumulatively rewritten with classifiers which will be used. But in particular, from the third form, you can see the commutator of arbitrary two elements of this layout over P is again a linear combination of elements of the vertex algebra, of the same type of element. And this sum is finite because AJB is 0 for J sufficiently large, because these are quantum fields, so A is the property of quantum fields that AJ applied to arbitrary vertex is 0 when J sufficient. So we get this remarkable huge Lie algebra, and this I mentioned it because this Lie algebra was mentioned in the talk of Chester van Eckeren, who used it to construct conformal blocks for arbitrary vertex algebra. And this was used subsequently in order to prove modular invariance of characters of vertex algebras, such as C2 dimension. So it's a very important layout. All right, the next thing which I want to explain. Moreover, this is a formal distribution. Regular formal distribution. It's first it should be the algebra. And secondly, collection, you should be collection of fields. The collection of fields is just A of T for all A and T. So it's a T collection of fields. And also there is a derivation, the T, such that not T rather F. And by translation lines, we have this property that commutator T is equal to the derivative. So this is the regular form. And this will be important for the subsequent discussion. All right. Next thing which I am going to prove is famous Borcher's identity, which also was mentioned. But nobody wrote it because it's very big. So this identity reads the following. For an integer z, A and B in the vertex algebra B, we have the following idea. If you take, as before, field corresponding to state A, I denote by A of C. If you remember, Jesser was denoted by Y of C, and Fede, I think, also. But this is a little simple notation, but sometimes this notation is more convenient. So you take A of C times B of W, you multiply by ICW of C minus W to C, which is expansion is the domain modulo C greater modulo W. And you subtract again the sign of the super case, B of W of P, I W C. So consider this expression. And then this expression has a very nice expansion. decomposition, given the decomposition theory. So the sum plus A inverse Maybe I should say that the original definition of virtues in the paper 1996 was a vertex algebra with Okotski-Gintry's terminology. It's the algebra satisfying virtues. And so with this proving the identity, we prove that our definition implies his definition. And it's very easy to prove the converse. His definition implies ours. And I find this really a remarkable, probably the most remarkable instance in algebra, when very complicated identities are derived from the very first and simple principle. After all, even the algebra is given by rather complicated Jacobi identity, but here you just don't have anything complicated with definition. And at the end, you derive something which is present. And also, let me remind you that this is just integrand for the definition of nth product. Namely, if you take residue in Z to this is definition of the nth product. So the identity gives expansion of the integrand in terms of the decomposition theorem via the data function. Here is actually very just one line. So the left-hand side is the local formal distribution in Z and W. Yes, and again, missing this position. So why it is local? Because if you multiply it by sufficiently high power of Z minus W, here you get IZW, some positive power of Z minus W. So you can erase IZW, because expansion of Z minus W to positive power is just itself. And the same here. So the result is that its commutator of A of Z with BW multiplied by big power of Z minus W, which is 0 Balakite. Okay. Okay, hence we apply decomposition theorem. Which says that the left-hand side, any local formal distribution, is equal to sum of Cj of W times the delta function, J's derivative of the delta function divided by delta. And also the decomposition theorem tells us what is Cj of W. Where Cj of W is equal to residue Z, the left-hand side, times Z minus W to sub z. But if you multiply by z minus w to sub z, you get a of z v of w, I z w, z minus w, n plus 2, minus n, I w, but what's written here is just exactly the product of n plus j product of a of w with b of w. This by definition of n's product. But now we have n's product identity, which says that this is equal to a n plus j b. Which exactly gives you the right answer. So this is it. I don't know actually many instances of use of the Borchers identity, except in representation series. It's really very important when you study the geoalgebra and related things, which perhaps I will mention next time. Now we will use lemma 6 in order to prove this kind of formally, of course, everything should follow from Borchers identity, because it's just the only identity which gives you everything. But there are some statements which I don't know how to derive directly from Borchers identity, so you have to play some tricks in order to do it. And this Q-symmetry is actually one of these things that I don't know how to derive. Okay, so next property of vertex algebra is Q-symmetry. If you apply a quantum field of vertex algebra to an element V, can you reverse it to write that it is actually V of Z applied to A? And the answer is you can. Namely, you have to take B not of Z, of minus Z, applied to A, but it's not quite right. You have to multiply by e to the Z. Apply e. This is it. Again, here should be sign. And I don't remember, as I mentioned, it is some people call it Koszul rule, some people call it Quillen's rule. I don't know exactly what was the first one. But the rule in superalgebra is this, that if you exchange two odd elements, then a sign appears. In other cases, no sign appears whatsoever. So if A and B are odd elements, then you should put here minus sign, because B went before. Otherwise, you just don't choose. Okay, proof. So okay, we take the locality, which is Z minus W. So and again, here you have to put sign. And you apply both sides to the line. And then use lemma 1. You have Z minus W to the n, equals WC B, and now we apply lemma 6. Namely, what we do, we conjugate B of W, namely, we insert here e to the zt, e to the minus. Then this conjugation by lemma 6, so e to the zt remains, but by lemma 6 you get here I WC B of W minus 3 plus applied use conjugation, then this thing you replace by minus 6 by B of W minus 0, then e to the zt remains inside. And this is double. Now the left hand side is obviously formal power series and W. There are some coefficients which are formal distributions. So here you can put W equals to 0. Here it is a little questionable because B of W minus Z. No, here also you can put it because no, you cannot, because since W is in the first place, you have if you have negative powers of W minus Z, then you will get negative powers of W. But if n is sufficiently large, then negative powers of W, there are only finitely many of them because this is a Lorentz series. And if it's sufficiently large, this becomes a formal power series. So if n is sufficiently large, it's again a formal power series in W. And this allows you to put W equals 0. I must confess, I almost felt a little uncomfortable with this argument.
So it's actually power series in both Z and W. There are no negative powers on either side.
Right. Yeah, because it's positive powers of Z, because of that. But if it's positive powers of W, anyway, I already said my opinion. I know another provision. And so we put W equals to 0 in the last expression. So if you do it on the left hand side, you get Z to the n times A of Z B, and the right hand side you get Z to the n times e to the ZT. Exactly what we claimed. E of minus Z applied to it. And of course after that you just cancel the Z to the n, which gives you Next very simple property, not that I will say, but I can, is that T is a derivation of all n products. And proof, I just say how you do it, and then you can easily just apply T to the expression A, Z, B equals sum to M. And we just put the definition of what is A. So you get T. But this you write as T A of G, apply to B plus A of G. And this quality applies to the next proposition says that all negative products are expressed in terms of minus first product. Let AB will be the minus first product of A with B. And we know that it is the right notation because it corresponds to the minus first product of quantum fields, which is normally always. Then they claim that all other negative products, I, A, minus M, minus 1B, again expressed in terms of this product, namely this T is at M, A, B, then if N greater than. So another product are expressed in terms of the normal order product. And proof is very simple. That simply we know that that by definition n minus first product of two fields is given by this formula that it is GG to n T. It was our original definition of this product. And by S product entity, and that's the identity which is the same, the TA or C. Implies the claim. It's a very trivial proposition, maybe it can be true. Alright, so we took care of all negative products. Now we'll take care of all non-negative products. N greater or equal than 0. This is taken care of by taking the generating field. Define the generating series, which we call lambda break. The generating series of all this non-negative. Actually, it is polynomial in lambda, again due to the property that A and B is zero when n is sufficient. large. And so we have just we have a free tube. Vertex algebra defines the following free tube. Of course, the space of the vertex algebra, the derivation, the reference vector, is a normally ordered problem as a lambda vector. And my goal is proof that this data is a kind of quantum Poisson algebra. Namely, if you take V vacuum and normally ordered product, you get a unit of algebra, which is almost commutative and almost associative. Like in the Poisson algebra, it is commutative and associative. And if you take Vt and lambda bracket A lambda t, then this defines what is called Lie conformal algebra, which I'm going to explain today. So it's a kind of Lie algebra stuff. And as in Poisson algebra, that these two operations are connected by a kind of Leibniz rule. But again, a corrected Leibniz rule, which he calls a big formula. So we get a deformed kind of notion for Poisson algebra. And of course, in the classical limit, you get what's called the Poisson vertex. This is the part. All right, but before doing it, since I already talked about the commutation formula, let me say something about the conformal weight. Because it appeared in all, I originally planned not talking about it, though it doesn't take much time. But since everybody talks about conformal weight, I have to say a few words. First of all, what is called a conformal vector of vertex algebra. A vector nu is called a conformal vector. I should say that this vector, sometimes it doesn't exist, sometimes there are many of them, so it is by no means a canonical thing. It's some additional structure, like complex structure of monomanifold. It could not exist, it could be many of them. If the corresponding quantum field to nu is the Virasoro field. So by now I'm sure that you remember for some C in F called central charge. Of this conformal vector. And again, by changing conformal vector, you even can change the conformal charge if you will. Secondly, minus first coefficient is the translation operator, second property. And the third property, that L0 is diagonalized. And its eigenvalues are called conformal vectors. Now let us see what the commutator formula gives us in this particular fluid. Maybe I should no, first of all, let me say the commutator formula what of a curve is the commutator of L of Z with A of W. It is sum J Lj minus 1A of W, then dW to J, it's because L0, because Ln in parentheses is equal to Ln because the shift. It is not here not minus shift. It is written there over here. And secondly, an equivalent without Fourier coefficient is that Lm just Lm is equal to sum J raised to 0 and plus 1 J minus 1 like it is. So this is what the commutator formula gives us when we field is L of C. Therefore, now what is the lambda bracket? With A. So this equal sum J greater or equal than 0. And lambda bracket consists of just taking this element and putting in front lambda to the j over j factorial. Simply derivative beta function is replaced by lambda to the j. So it gives you sum lambda to the j over j factorial L j minus 1. Okay, let me write what is it. If j is equal to 0, you get L minus 1 applied to A. But the property 2, it is just TA. When j is equal to 1, you get L0 applied to A. But L0 applied to A, if A is eigenvector, is eigenvalue times A. So you get delta A times that. And plus the higher power sublime. Of course, if A is eigenvector of L0 with eigenvalue delta A. Or from this formula, we get that in particular, taking coefficient of z with minus 2, which is L0. We get that L0 bracket with B with A of z is equal to the derivative plus delta A applied to A of z. An operator H satisfying this property is called an energy operator. So in particular, L0 is an energy operator. So in order to talk about conformal weights, it suffices just to talk about energy operator, which, for example, at critical level exists, but conformal vector in this case doesn't exist. So for Kac it's very important. So we still have conformal weights, though we don't have their sort of Okay, and a very important observation if we write an eigenvector of H, sum n without parentheses, equals minus n minus delta, then n of course should run over minus delta plus z. Then commutator of H is n is equal to minus n minus 1. It is simply because somehow delta is decreased. It's because because A in parentheses is in a very simple way related to A with operator, namely because n minus delta A plus 1. For example, A0 in parentheses, delta. That's why people write fields in this form, because then you have this commutator with energy operator without it.
So is that here what's H?
H is in H is operator satisfying this condition. Let me write it again. H Z is equal to dz delta A times L. And what I said is that L0 by definition is an energy. And this is one of the ways to construct energy operators, but there are different ways.
Energy operator is something satisfying that condition, and so L0 is
Yeah, energy operator is arbitrary operator satisfying this condition
by definition.
by definition. And the claim is that if you write A in this form, then commutator with energy operator will be generated. And this actually is equivalent.
Sorry, do you mean if we write AZ equal or
A of Z.
A of Z? A of Z.
But where delta A's are what? Just arbitrary.
No, delta is equal to eigenvalue delta A. Yeah, maybe I should write it.
Yeah,
Delta
but
is eigenvalue A.
so delta A's are the eigenvalues of H.
Right. Yeah, I wrote it. So the operator is diagonalizable operator. Yeah, I forgot to say. Because of zero was so diagonalizable operator satisfies this limitation. Or equivalently, the diagonalizable operator which satisfies this limitation. And this doesn't involve this is true for any. Not an eigenvalue. Okay. And now a very simple property of conformal weights. Is the following. It is the vacuum vector is zero conformal weight. If you apply C to A, you get delta A plus 1. Applying C shifts conformal weight by 1. And finally, if you take nth product, it's equal to delta A plus delta B minus n minus. I don't know if delta. Yeah, it's the first two properties are in this straightforward. Let me prove the last one. What we do is we apply H to A and B. But it is the same as apply operator H to AM. Take a commutator and apply it plus an H applied to B. But HAM is by
Minus
is equal this is equal to delta A minus n minus 1 times and this gives you delta T. And this, yeah, because yeah, it follows from the definition. This, if you write it in Fourier coefficients, you will exactly see that it's delta A minus 1. And so this proves. Now, remark. Note that for the Virasoro, rather we denote it by nu lambda nu is equal to t plus 2 lambda nu plus lambda cube c times the y. But remember the definition of the conformal wave. This is one of the equivalent definition. So from this we conclude that the conformal weight of the Virasoro is equal to 2, because this is coefficient of lambda. Therefore, Virasoro we have to write some ln z to the minus n minus 2, which we've been doing all the time. So this is consists of which we've been doing. And the second remark is that conformal weight is a good bookkeeping device. Namely, you remember A lambda B is a generating series of 4 products, lambda n factorial, A and B. And if we put letting delta lambda equals 1 and delta t is equal to 1 and delta A is equal to delta A, we see that all terms, all summands have conformal weight delta A plus delta B minus 1. Because what? A and B has conformal weight delta A plus delta B minus n, but lambda to the n have conformal weight n. So n and n cancels out. So in other words, this is the whole right hand side is homogeneous with respect to conformal weight of degree sum of conformal weights minus 1. In the case of Virasoro, conformal weight of Virasoro is 2. So all terms have to have conformal weight 3. And indeed, this has conformal weight 1, this 2, so all have it 3. C is a constant, vacuum has 0, and lambda cube has conformal weight 3. So all, and this allows you to compute all possible brackets of the fields, all possible terms. They should obey this rule. Should have the same. And it's a very important device in the theory of okay. Now, okay, let me introduce the last thing. Okay, I introduce the lambda bracket. It's actually here. And so now we return to terms of the study of lambda bracket. You remember we have this Q, we already studied normal lambda product to some extent, but this we didn't discuss at all. So the question is what does it say? So now we return to the formal distribution culture. And of course everybody you know that Fourier transform replacing is equal to so definition Fourier transform denoted by R lambda G is a match from the space of U value from distribution to the space of formal power series of lambda defined by as follows that f lambda z is equal to residue e to the lambda z a to z. It's clear that it's formal power series because lambda is powers. Okay, let me finish with its properties, which is straightforward.
F lambda z of A
What?
applied to A in the left hand side.
Yes, okay. Properties. And it's a nice choice. Yeah, so I wrote here four properties. So first, what happens if you apply derivative? And it's the same way as usual Fourier transform. It multiplies the Fourier transform by minus lambda. Second, if what is Fourier transform applied to the derivative of the delta function? Get e to the lambda w lambda 2 third property that lambda equal to a minus is minus z minus lambda. And the fourth is that if you apply f lambda z to e to the z you get f z lambda plus 2. Yeah, this equality doesn't really make sense. You have to assume something which falls in the situation. Namely, if T is an endomorphism, such that yeah, T is endomorphism, and A of Z is not an arbitrary form distribution, but actually it's a Laurent series. So we will need this. So all of them are completely straightforward. Let me just check. This is probably the most complicated bit, the most famous. So let me check. What if you apply Fourier transform to the case derivative of delta function. Of course, it commutes with Fourier transform because Z and W are independent of Y. So it's just Z W is K applied to the Fourier transform of the delta function, which is basically e to the lambda Z delta Z W delta Z. But then what is this? With the property of the delta function, this is equal to e to the lambda W. Right? Because delta function, because rating of delta function times a function in Z is the same function in time. So you have to apply dw to the k to it, which is lambda to the k e to the exactly. And all other properties, so it's the same. Okay, so I think that any questions? And please, the writers do write.